We're now going to continue learning about combination circuits. Remember that our goal is always to take a combination circuit and reduce it to a series circuit so that we can conduct an analysis and determine the total resistance and current and voltage through each element of our resistor circuit. Let's go over the rules. Remember, we have our mnemonic device, Vir-Sacca-Pekara, which helps us to remember the properties of resistors in series and parallel. So remember, Vir-Sacca-Pekara. And we have a chart here as a study guide, just as a reminder. So voltage in series is going to add. In series, current is constant. And resistance adds. For parallel circuits, voltage is constant. Current adds. And for resistance, reciprocals add. So that's a quick review of our rules before we take a look at our next example circuit. Okay, I've taken the information out of the VERP table, the resistance for each resistor, and labeled it accordingly, as well as the total voltage, which is 60 volts in this problem. I now have to take a look at this circuit and figure out how I can break it down so that it ends up being just a series circuit. So right away you see you have a junction. You can go through R1 and R2, or you could go through R3. So you have choice. So right away you might be inclined to decide that that's a parallel circuit. But actually, there's a step before that. So let's say that you did decide to go through R1. You'll notice that you also have to go through R2. So if I go through R1, I don't have a choice about going through R2, which means that R1 and R2 are in series. So the first step is actually going to be to break that down, and we're going to create a box around that. And I'm going to put an S in the box to indicate that those two are in series. And I'm going to write V, I, and R because we're going to want to determine those quantities for this box. So we have a 10 ohm resistor and a 5 ohm resistor, and they are in series. So what are the rules for resistance in series? It adds. So 10 plus 5 is 15. So we now pretend that that purple box is just a single resistor with resistance 15 ohms. Now that we have isolated R1 and R2 and are treating them as a single resistor, we go back to that first junction. At that first junction, we did have a choice. We could go through this purple box, or we could go through R3. That means that R3 and the purple box are in parallel with one another. So to indicate that this blue box or teal box is parallel, I like to put a P. I'm going to write V, I, and R. So because the purple box and R3 were in parallel, and we want to find their equivalent resistance of the purple box in R3, we need to look at the rules for resistance in parallel, which is reciprocals add. So in order to do that, you have to do 15 to the negative 1 plus 10 to the negative 1. And then remember, you're going to hit your answer to the negative 1, and you are going to get 6 ohms for the total resistance of that teal box. So if you take a look now, we've taken a circuit and we have reduced it to be a series circuit, specifically a series circuit with 3 resistors. So we have our 60 volt power supply, we have our teal box, which is just going to be 6 ohms. We have our 8 ohm R4, and we have R5, which is 6 ohms. So because this is a series circuit with 1, 2, 3 resistors, and we know the rules for resistors in series are that they add, we can simply add 6 ohms plus 8 ohms plus 6 ohms to get the total resistance of this circuit. And when we do that, we get 20 ohms. So we're going to fill that in the verb chart. Now that we know our total resistance and we know our total voltage, recall the verb chart is laid out. V equals IR and P is equal to IV. So we can find our total current down here. So 60 divided by 20 is 3 amps, which means that the total current coming out of that power supply is going to be 3 amps. So now we need to decide where do all 3 amps have to go. So let's take a look for a moment at that drawing at the right. All 3 amps come out of the power supply. Do they have to go through the teal box? They do. Do they have to go through R4? They do. Do they have to go through R5? They do. So that means the teal box gets 3 amps. R4 gets 3 amps. And R5 gets 3 amps. So in the chart, I can fill in R4 and R5 for 3 amps. But the teal box is not actually a resistor in our circuit, but rather a combination. So I'm going to indicate that by putting the 3 amps in the teal box for current. The next piece of the puzzle to fall is if I know the current in this teal box, the resistance in the teal box, I can multiply them, 3 amps times 6 ohms, to get 18 volts. Because the voltage in the teal box is 18 volts, and the teal box is covering up a parallel circuit, I know that voltage is what's constant for whatever that teal box was covering up. So what was it covering up? Well, it was covering up 2 things. The teal box was covering up R3 and the purple box. And because voltage in parallel is constant, I can take that 18 volts, I can put it in the purple box, and I can take that 18 volts and I can put it on R3. So I can actually fill in the value for R3 voltage in the chart as 18 volts. The next thing I have to do is take a look inside the purple box. I need to find the current inside the purple box. And I'm going to do 18 volts divided by 15 ohms to get 1.2 amps. Now, that purple box was covering up what kind of circuit? Well, the purple box is covering up R1 and R2, and because if you go through R1, you must also go through R2, they are in series. So the purple box is a series circuit. If you check your rules in a series circuit, what is constant? And the answer is current, which means that both R1 and R2 must both get the full 1.2 amps of current. You can see we now have either something in the voltage column or the current column for every single resistor, and we can proceed to fill out the chart. So 10 times 1.2 is going to give me 12 volts. 5 times 1.2 is going to give me 6 volts. 18 volts divided by 10 is going to give me 1.8 amps. And for R4, 3 amps times 8 ohms is going to give me 24 volts. And in R5, 6 ohms times 3 amps is going to give me 18 volts. We can then go through and do our power check. Remember, power is equal to current times voltage. So 12 times 1.2 is 14.4. 6 times 1.2 is 7.2. 18 times 1.8 is 32.4. 24 times 3 is 72. And 18 times 3 is 54. So we're going to add all these up, and we're going to get 180 watts. We're now going to check that. So total power is equal to total current times total voltage. So our total current was 3 amps. Our total voltage is 60 volts. So that's going to give us 180 watts. And you can see that when we added and when we multiplied our totals, we got to the same value, which indicates that we did this problem correctly. So, to review, we took the circuit, we combined elements that were in series, R1 and R2, treated them as a single resistor, combined that purple box as though it were its own resistor with R3 because they are in parallel, and then we treated that teal box as though it was its own resistor. And that allowed us to reduce this combination circuit to be a series circuit. And we were able to find the voltage and the current for each resistor.